Log on, tune in, find out. Another good idea from Cambridge.
Numerical homogenization method.
Okay, thank you, Claude, and thanks to the organizer to give me the opportunity to give this talk here. So, as said, that's the title of my talk, and here's the outline. So I will start with some example, explain a bit what we are doing, what numerical homogenization is. So it will be a short introduction, also a very brief introduction to homogenization. So for those who do not know what that is. Then I would like to focus on the analysis of numerical homogenization method, and I would like to emphasize on the fact that numerical homogenization methods are based on FEM with quadrature, in fact, okay? And I will show all the results for elliptic multiscale problems. Then I will quite briefly show some new result on wave equation, and I would like to insist a bit more on nonlinear multiscale problems. Again, to see the relation between this numerical quadrature scheme and the analysis of numerical homogenization method. So that's a very recent work, joint work with Gilles Villemar, which is a postdoc with me, and yeah, part of this work is still work in progress. Okay, so I start with an example. So that's an example. Would like to compute the heat distribution in a microprocessor, which is depicted here, made of three components. We have the plastic package here, we have the chip, and we have the lead frame here. Okay. So often, to have good properties of heat dissipation, the plastic package and the lead frame are made of composite materials. Okay, and that's typically depicted here. So these composite material are, say, two materials mixed together, and the mixture looks homogeneous at the microscopic scale. Here the microscopic scale would be the scale of centimeter, but it looks heterogeneous at the micro scale. Here the micro scale typically would be of size micrometer. Okay, so what we want to do, that sets the scene, what numerical homogenization is about, is try to understand the macroscopic property of this material. So the macroscopic property, for example, of heat dissipation. So here, what is depicted here is a macroscopic mesh. Okay, even though it doesn't look so macroscopic, it's a macroscopic mesh. And within each of these macroscopic tetrahedra, which is depicted here, we have a so-called sampling domain. In some literature, it's called representative volume elements, which is of size much smaller. Typically, the size of this box is related to the size of the microstructure. Okay, and we like to test the microstructure in this sampling domain. Okay, so if the microstructure changes from one with the smooth variable, with the x variable, we have to test it at several points. We have to test it maybe in each macroscopic tetrahedra. Okay. So here in this example, we have three components. We have three tensor, which oscillates. The chip tensor does not. The tensor for the chip does not oscillate. So we solve the heat equation with Robin boundary condition. Okay. So immediately, and I will insist on that during the talk, we see here that we have already two numerical parameters. Okay, we have the h, that is the scale of the macroscopic tetrahedra here, and we have the small h, which is the scale of this box here is discretized. Okay, you should now consider this box as being made of small finite elements. Okay, it's discretized, and h is the typical size of a small elements in this sampling domain. Okay. So let's look at some numerical examples. So I take some fake microstructure here to do numerical comparison, and I have here the order of the microstructure 5 to 10 to the minus 5, okay, and I do fine scale resolution of the problem. It involves 22 million tetrahedra, okay. On this side, I do what I will explain later on, a numerical homogenization method. It's based on 10 to the 5 macroscopic degrees of freedom, okay? So the cost here will be the microscopic degrees of freedom times what we do in each sampling domain. And I will come back to that later, okay? And on that side, I show finite element method. If you do not resolve the structure, you take basically the same microscopic grid that I had here, okay? But you just sample one point in each tetrahedra, and you see that you don't get the right effective conductivity. The medium is looks much too dissipative on this side here. Okay. So there are several questions. I will come back to that. The question of numerical homogenization. I will not address, of course, all the issues with that. I will address one of the issues. And here, one question that we can ask is how should we set the relation between the small h and the capital H here to have optimal accuracy with minimal computational cost? Okay, let's take an example. We have here a macroscopic, we have here, a numerical simulation. Okay, it's made of the mesh that I just had here. It's made of a mesh with 8 times 10 to the 4 degrees of freedom, macroscopic degrees of freedom. So if you want to have a refined calculation, what should we do? Should we refine the macroscopic tetrahedra? It will lead to more than millions tetrahedra here, within each tetrahedra doing sampling domains, okay? Or should we refine the mesh here, okay? So the a priori error estimate that we have tells us that we have to refine the microscopic mesh, and indeed, if you do that, you have a better accuracy of your simulation, okay? So if here, instead of doing that, we would have done the choice of refine the macroscopic mesh, we would end up with a much, much more expensive problem, okay? Many millions tetrahedra, and in each tetrahedra sampling domains, while in fact, we do not need to do that. We just only need to refine the microscopic mesh, which is also costly, of course, but that's the most efficient way to proceed. Okay. So here I show again what I'm just talking about. That's the chip now with a realistic microstructure. Here, fine-scale solutions are impossible. Okay. We need 10 to the 11 degrees of freedom, and here we have the simulation with various microscopic degrees of freedom. Okay. So here we have another example. Example is example of a wave. Okay, so we have an expanding Gauss pulse. Here on the right side we have the homogenized solution. I will tell in a minute what that is. Here we have the numerical homogenization solution. Okay, the so-called the FEHMM, which stands for finite element heterogeneous multiscale method, and the medium is anisotropic, and we see how the pulse evolves, where we compare the numerical homogenization method and the homogenized solution. Okay. So as I said, I will do a very, very quick introduction on homogenization. So what is the problem at hand here? The problem here that I'm considering is a PDE, okay, where, as I showed in the previous example, the medium depends on small scale, okay, and that's depicted here by the d epsilon coefficient. Okay, so as we don't want to solve the fine scale, we would just like to have an effective solution. That may not be always what we want in application. Huh? Sometimes maybe you want some information on the small scale solution. Okay, that's another story. But suppose that we just are interested in the coarse behavior. Okay, so the question here is to ask if there exists, if this collection of U epsilon solution converge in some sense to an effective U0 solution, and asking if there's an equation for U0. If I take the analogy with the composite material that I had before, so composite material are materials which have maybe two components mixed together. Okay, so the homogenization, the word homogenization comes from there. We would like to homogenize this material so that they are more and more homogeneous material. okay? And so we are not interested in the properties of each of component of the material, but of the homogenized material, okay? So mathematically we can, of course, go epsilon to 0. In practice, that's not the story, okay? So I take an example. The example is this elliptic multiscale problem, okay? So I have a standard elliptic problem here. I suppose that A epsilon is uniformly elliptic and bounded, so there exists a unique solution. Okay, so that's completely classical. The only problem here is a computational problem, of course. If I want to solve that with FEM, I have to resolve the small scale here, and that's not possible, okay? So here I have a bound for the family of U epsilon solution. They are all bounded by constant times F, and I have also a bound for the family of flux, okay? So now, weak convergence theory tells us that there is a weak convergence of U epsilon to U0 in H10, and a weak convergence of C epsilon to C0, okay? And then we can pass here to the limits, and we have this equation, divergence of C0 is F, okay? So that's all almost for free, okay? So the only problem, and is why we are working in this area, otherwise there would be no homogenization theory, is in general it's not easy to relate the macroscopic flux to the macroscopic gradient of the homogenized solution to the macroscopic flux, okay? So the proportionality, the relation involves a tensor, A0, which usually cannot be computed analytically, okay? So what one should keep in mind for people who do not know about homogenization theory is that this A0 is not a simple average, as I showed in the very first picture, where there was a picture of a chip with naive average, okay? So A0 is not a simple average as arithmetic average or harmonic average, okay? Except in one dimension where it's really a harmonic average. So now a multiscale problem, what we'd like to do. So we have again this PDE, which depends on small scale. We'd like to compute the effective problem, okay? But the effective coefficient D0 is unknown, okay? So what is numerical homogenization about? We consider a macroscopic discretization of our domain, okay? It's made of elements K. These elements K are depicted here, quadrilateral and triangle, okay, with diameter much larger than the small scale of interest, okay? So what we would like to define a finite element method at the microscopic scale, okay? The finite element method could be a discontinuous Galerkin finite element method, a mixed finite element method, whatever. Here you import all what you know about finite elements. Okay, the problem is that the operator LH is unknown because you don't know the effective coefficient, okay? So what you will do now, as I explained again in the first picture, in each of these macro elements, you will test the microstructure in some sampling domains. So the sampling domains are not located at arbitrary place. As you see, it's at some so-called quattro points, okay? So the idea, and I will go through this talk with this idea, we put here the sampling domain at quadrature points that are defined by what we would do if we would do numerical quadrature in the homogenized solution, okay? And instead of evaluating here the data that we don't know, we set a sampling domain, okay? And we solve yet another finite element method, that's the micro finite element method, okay? So here I have a micro solution. It's constrained, I will explain that later on, by the macroscopic state, okay? We solve, in fact, the original problem. So the only data that we need is the original data. It could be given by a stream of points. Doesn't need to be even a function, okay? And so we solve here a microscopic problem, and we'd like that the somehow proper average of the microscopic solution on the sampling domain gives us what we need, the average of the homogenized or macroscopic solution in the macroscopic elements, okay? That's the idea. Of course, in each sampling domain, as I said before, we have to set a finite element method which lives on a certain domain, which has a certain mesh. The small mesh is H here. Okay. So there have been many, many people working in this area. I list here a few group and a few class of methods which deals with numerical homogenization. Okay. So I come to the second part of my talk now. So I will briefly, or not so briefly, review some results on elliptic multiscale problems. Then I said I will come to some new results. Okay, so let's focus again on this elliptic problem. Okay, multiscale elliptic problem. We suppose that we have an effective problem which exists. Okay. So once again, what we could do here, and sometimes it's possible, is just to do a standard finite element. So we solve that problem here. We take a triangulation, and the only problem is that the error, in fact, is say with piecewise linear finite elements is O of H divided by epsilon. Okay. Why? If you do finite elements, H1 convergence result, you know that you have a semi-norm of the solution in H2, and this solution usually goes like 1 over epsilon. Okay, so that you have an error of H divided by epsilon. So that H must be taken much more than epsilon if you want to have a convergence. Okay, so let me now. It's the only slide where I go through really the details of the method. Later on, I will just take the bilinear form as granted. Okay. So what do we do here? So as I said before, we take a macroscopic finite element space here. Okay, omega is my domain, tau H is my triangulation. Okay, my macroscopic triangulation. Here, H is arbitrary, can be much larger than epsilon. Okay. So now, as for numerical integration, what I would do, I would divide that in elements, and within each element, I would evaluate the data on the integration points. Okay. So as I said before, I cannot do that here because I don't know the macroscopic data. Okay. So what I would do, I would compute this contribution here. That's a contribution which lives on an element, a given element. You see here what we have as ingredient are WKJ, and the location of the sampling domain are located around the point xj. K delta j, sorry, is located around the point xj. Okay. So WKJ and xj are quadru points. Okay, are quadru points that you would use in standard FEM with numerical integration. Okay. What is different here that for each macroscopic function here, we have a microscopic function, and this microscopic function minimizes an energy given by the original problem. Okay, that's the energy here. Okay, it's constrained by the macroscopic variable. And another way to say that is that it solves the boundary value problem here, constrained by VH, which is the macroscopic function. Okay, there's slight subtleties here that we have to take VH lin. We linearize the macroscopic function around the quadru points. But I don't want to enter into these details here. Then okay, suppose that works. Then we have a variational problem. Now it's just defined on the macroscopic space. Okay. Of course, I have to say what this micro finite element space are. Okay. And in fact, the choice of this micro finite element space here will set the choice of the coupling between the macroscopic and the microscopic variables. Okay. So the case of periodic data, we can take periodic boundary condition, and even if you take the sampling domain exactly the size of a period, that's the optimal choice. Okay, but you could also take artificial boundary condition, like Dirichlet boundary condition. That's also a possible choice. Okay, it's very easy to show that the macroscopic bilinear form is coercive, so there exists a unique solution. Of course, here to show that you need to have some properties of this quadrature points. Okay, and the properties are the properties that are used in FEM with numerical integration. There also you need to have a bilinear form, a numerical integrated bilinear form which is coercive. Okay, so upon well-chosen quadrature points, the quadrature weights, you have a coercive bilinear form. Okay, and the convergence analysis, you have several errors. The macroscopic error comes from the h here. The microscopic error comes from the small h here. And the modeling error, okay? And I will not insist too much on the modeling error, but I will already say here, if you, for example, take a sampling domain with, say, in the simplest case, you have a periodic problem, but you don't know the period. So you embed your periodic problem in a larger box, okay? And then, okay, make no necessary sense to take periodic boundary condition. You take simple Dirichlet boundary condition, okay? And then you do two errors. You do errors because you introduce wrong boundary condition. You don't know the boundary condition on this larger box. And you make an error because you average the energy over not exactly integral multiple of the period, okay? And there have been recently, I will come back briefly to that, some interesting result in that direction. Okay. So I will, again, take the various bilinear form that you have in hand, and I will try to reformulate this numerical method to see a bit how we can analyze that. Okay. So B0 here, that's the exact bilinear form. Okay, it's the bilinear form of the homogenized problem. Okay. B0H is the finite element method for that problem with numerical quadrature. Okay, that's standard. Okay, this bilinear form B bar H is exactly the bilinear form that I defined before, but you see I didn't put an H here. Okay, so I assume that the micro calculation here are exact. Okay, and finally we have the fully discrete multiscale method where you have parameter H here and small parameter H here. Okay. So now let me again reformulate this, the two last bilinear form. One can show that there is an energy equality between the average of the small scale function weighted by the size of the sampling domain with the average of the macroscopic function to which they are related. Remember that VH minus V minus VH V is constrained by V capital H, okay? So we have an energy equivalence, and we have here an unknown tensor, which is A bar 0K, and that encodes the calculation that we do on the sampling domain. Okay, so that can be shown here, and likewise for the fully discrete method, we can show this energy equality. Okay, so now I can rewrite again my bilinear form. I have here again the bilinear form with numerical quadrature for the homogenized solution, the FEHMM with exact microfunction. Now it looks very similar to that, okay? Just the tensor now is of course different. And again here we have the full discrete. We have again, we see that it is a FEM with numerical quadrature, and we have some approximation of data here, of course, okay? So here now the micro calculation and the micro function comes into that tensor here, okay? So a priori estimate, so what you do, you decompose now the error into U minus U0H. That's the standard, that's the homogenized solution. That's the solution of this bilinear form here, okay? FEM with numerical quadrature. And then you have FEM with numerical quadrature minus the solution that we are looking for, okay? So the first part here is given by standard result, and there are not so many. For elliptic problem, there is one result. It's by Raviard and Tiarlet. Okay, they have shown that provided enough regularity, provided good quadrature points and quadrature weights, you can have the optimal convergence rate. Okay. So we have all been using this result, but in fact they are not trivial results. And when these results do not exist, we suffer a bit to derive them. Okay, and I will come back to that in the nonlinear case. Of course, here we make an error. The error is what the part here. And this error can be estimated with Strang type arguments. Okay, that's the supremum between the two bilinear form. So now it boils down to the difference between these tensors. Okay, so that's the homogenized tensor at quadrature points, and that's the numerical equivalent that I showed before. Okay, and that can be estimated, for example, in the periodic case. You need some regularity here. I will not go into detail with that. And this can be estimated with as h of epsilon to the 2q plus a modeling error. So here are several comments. We have 2q here. It means that if you have piecewise linear finite elements in the microscopic method, we have h of epsilon square. Okay, so we have a better convergence than for standard finite elements. It comes from the fact that we very roughly said it comes to the fact that in the original linear form here we have two errors which multiplies, in fact. Okay, two finite element errors which multiplies. Okay. So as I said, the macroscopic error is a result by Ciarlet and Raviard. Okay. The modeling error. So if you have in a best setting, okay, when you have a locally periodic coefficient, one can show that this modeling error disappears. Okay. So we only really have numerical parameters h and small h. Okay. Otherwise, we have resonance error. Okay. And here, that's not a numerical discretization error. That's error, as I said, because you take wrong boundary condition on wrong sampling domains. Okay. Also, there are several results that I cite here for this resonance error, and recently a quite interesting paper of Antoine Gloria, okay, who showed much better error rates for the modeling error, provided that you take appropriate that you define appropriately your sampling domain with some modification of the original problem, but I don't want to go into details here. Okay. So just a warning is here we have h of epsilon to some power, but h of epsilon in fact is just related to the microscopic degrees of freedom. Okay. So if you have a problem which is where epsilon decreases, okay, it's not the numerical cost here is not depending on epsilon. Okay, it's depending on the microscopic degrees of freedom and the macroscopic degrees of freedom. Okay, and then they have to be set according to the relation 2ql plus 1 or 2ql. Okay, C of course is dependent of epsilon, otherwise there will be no result here, but depend on the upscale solution. Okay. So here again I listed this result here. So let's show these results are sharp. Let's look at the simplest problem, periodic problem, where we have no modeling error. Then it boils down to, for the L2 norm, for example, to do that kind of estimate. Okay. And as I said before, in terms of degrees of freedom, that's one of the macroscopic degrees of freedom plus one of the microscopic degrees of freedom. Okay. And what you show in this numerical example there, on the x-axis, it's the macroscopic mesh size. Okay, on the y-axis is the error in the L2 norm, and the macroscopic mesh size decreases from right to left, and each of these lines is with a different microscopic mesh, which is fixed. Okay, so if you fix, for example, here I start with 4 points in the microscopic mesh, so you quickly reach no convergence at all, which means that the dominant part, of course, is this part here. If you refine the microscopic mesh, you get a better convergence, and so on and so forth. And only if you refine the two mesh simultaneously with a good rate, you can have the optimal convergence. Okay, that has a direct implication on the complexity. For example, in the L2 norm, the complexity is not linear; it's superlinear in the macroscopic degree of freedom. Likewise, in the H1 norm, it's not linear; it's superlinear in the macroscopic degree of freedom. Okay, so. There are many papers when I read that for the sampling domain it's sufficient to take 8 points per wavelength or something like that. That's not true, right? I mean, you have really to, depending on the accuracy that you want, you have really to refine also the microscopic degrees of freedom. And in real computation, what takes time is this n here, right? I mean, it's the fact that we have really to solve accurately the microscopic problems. Okay, so let's now go to a time-dependent problem. So we have now same problem as before. is the wave equation. Okay, again we have here an oscillating tensor. Okay, take usually boundary initial condition here, and okay, some boundary condition. So the multiscale method is as before. I just add some time. BH is the bilinear form that we had seen before, that we have seen before. Okay. So how does the a priori estimate go? So we have here result in the L infinity L2 norm and the L infinity H1 norm. Okay. So again, the analysis, we can use result on the wave with numerical quadrature. They are by Baker and Dugalis, 76. Okay. And then strength type lemma. Here we have to see that the error that we do in the microscopic scale are propagated in the right way through the scheme. Okay. And it turns out that one can obtain this result, HL plus 1 plus RHMM, which is exactly the same, has exactly the same structure as before. Okay. So here again, we can now, in some case, understand how this error behaves. And in the simplest periodic case, we have the same rate as before. Okay. Again, these results are sharp. That's a similar simulation as before. Okay. Here we have in the L2 norm again, H here, the L2, L infinity L2 error here, and for various equalization of the microscopic scale, we see that the convergence only obtained if we refine both scale at the same rate. Okay. Let's take an example of with a tensor which is not periodic, which has jumps, as depicted here. Okay. So we take an initial condition, a right moving Gaussian pulse. The data are here. Epsilon, the delta is the size of the sampling domain. It is chosen as to be epsilon. Epsilon is one of the period that we have here in this signal. Okay, the microscopic mesh size is 10 to minus 2. The microscopic mesh size is 10 to minus 4. And that's the time step here. And we'll compare the result to the reference solution. Be careful, we don't have result here comparing the reference solution to the fine scale solution. Okay, we have result here only error estimates compared to the homogenized solution. Okay, so let's see what happens. So in blue it's the reference solution, in red it's the HMM solution. Okay, that's what we obtained over time, from time 0 to 3. Okay, and in blue now here is the yeah. So again, now that's okay. That's the final result with the multiscale method, and here just a result where we see that again naive averaging is wrong. So in red it's naive averaging, and in blue it's the reference solution. Already on this short time we are completely off the wave. Okay. So that's again to insist that naive average is wrong. Here there's a big warning. Okay. Because I showed picture where I compared that to the exact small scale solution. Okay. But the numerical method does capture the homogenized solution, okay? And it does only approximate the small scale solution on short time O of 1, okay? That's because the wave, the energy of the small scale wave and the energy of the homogenized wave are not the same, okay? So for longer time, you see dispersive effects, and so you should derive other homogenized model with higher order terms, okay? And that's currently some work in progress to have a method which captures longer the fine scale solution on longer time. Okay, so now we'd like to come to nonlinear multiscale problem, and we'll spend a bit more time on that problem. So what do we have here? We have here an elliptic problem, a nonlinear elliptic problem, and it's a non-monotone problem, okay, of this type here. So first result for the numerical analysis, numerical homogenization method was by Yiming Zhang, 2005. And there's also a result for the so-called multiscale finite element method developed by Tom Howe and co-worker in 2007. And the idea that it's really related on the paper of Xu, Sinum, two-degree discretization. Okay, the idea there is that you linearize the problem at the exact solution, and you look the numerical approximation of the linear problem, which is very close to the numerical approximation, to the numerical solution of the original problem. Okay, so several questions that we would like to address. The first question is the full discrete analysis. That was not mentioned in the two paper. The second question is L2 convergence results. So there were only H1 convergence results. It's by no means trivial to have the L2 results. Third is quadrilateral elements. So here it was only done for simplicial elements. And again, I would like to put a warning here. It's not trivial at all to extend the result that I've given here to quadrilateral elements. I don't know how to do that with the technique used there. Dimension 3. So if you look at the results here, they rely on a bound for the 2D discrete Green functions. I don't know it is bound in 3D. Okay, so I don't know how to generalize these results as they are done then in 3D. And finally, uniqueness of numerical solution depends on capital H and small h. Okay, that's the kind of question that we would like to address now. So first, I would like just to stress, this problem here is important. Important for many. Wait, phrase. Important ingredient for many problems. It enters in the Stefan problem, Richard problem, for example. Okay. So, as I said before, you have seen in the elliptic case, in the wave problems, we are relying on results from numerical quadrature derived by Sierlet-Raviard or by Baker-Dougalis. Okay. The natural question here is to do the same methodology. Okay. Take numerical quadrature for FEM with for nonlinear FEM, and then try to see with strong type arguments how we can estimate the error due to the nonconformity of the method. Okay. No, sorry, that's no time dependent now. Oh, it is a typo. Oh, sorry, thanks. Thank you. Yeah, that's I copied from the last slide. No, that's just stationary problem right now. Yeah. Thanks for the comment. So let's look at the. Let's forget now. Let's for a while forget about the multiscale nature of the problem. Let's just look at that problem here. Okay, and let's look at the result that exists for that problem here. So there are some results. So the first analysis for the a priori analysis for the finite element method is by Douglas and Dupont, 1975, a beautiful paper. Then there is a result of Nietzsche for L infinity estimate. Then there are many results that I don't quote here in finite elements. Now we ask result on numerical integration. So the first result that I know is by Feistauer and Zeniczek. FEM with numerical integration. Here they take a more general problem. They take a problem depending on U and grade U. Okay, but they do an assumption that it's strongly monotone. Okay, and this problem is not strongly monotone. Okay, for all possible coefficients that you think of, that you can think of for AU, it will not be monotone. Okay. So then later on, they did a FEM with numerical integration for non-monotone problems, exactly this kind of problems, but they do not have convergence rates. Okay, they just show that the numerical solution should converge, but they do not have convergence rates.
How can we guarantee that the problem has solution if it is not monotonic or if it's not?
No, it's. I will just next slide. I will just summarize the result, which is known about the solution. Okay, I will just summarize that. Okay, so I come to that. So the goal is a priori analysis with convergence rate in the H1 and L2 norms for FEM numerical quadrature, full discrete a priori analysis for the FEM FEHMM, and uniqueness of the full discrete numerical solution. I will come to the next slide to your question. Okay. In fact, if the coefficient is if A epsilon is elliptic and bounded and is Lipschitz continues, you have a unique solution of your problem. Okay. Yeah. Okay, so the problem at hand is here. That's the binary form. Okay, FEM with numerical quadrature. That's as I explained before. Okay, so now we have no multi-scale. We just have one scale. Okay, and just listed here the assumption that we do on the quadrature formula Q1 and Q2. Okay, you don't have to read this assumption. I just want to stress that it is similar assumption to FEM for linear problems. Okay, that's the same assumption taken by Sierlet-Raviard. Basically, the first assumption gives you gives you coercivity of your method, but the second assumption gives you the accuracy that you need. Here the R is either either simplicial elements or quadrature elements, okay? And there are a bit of different conditions for simplicial or for rectangular finite elements. Okay? So we have now the exact problem here. We have the Fermi numerical quadrature, and we want to prove optimal a priori error estimates. So I come now to the question here. So I take here a tensor, okay? It's not a scalar and depends on x, so you cannot do Kirchhoff transformation. Okay, so if you assume that A mxs is continuous, you assume that the tensor is Lipschitz, okay? And as I said, you have ellipticity. Then the nonlinear elliptic problem has a unique solution. Okay, the first result is by Douglas and Dupont and Serrin, and there is a recent result. I mean, there is a recent quite different proof in a book of Shippo in 2009. Now, if you assume only 1 and 3, okay, Q1 and Q2, so Q1 and Q2 were the result for the numerical integration, then you can show that for all H, the nonlinear problem with numerical quadrature has at least one solution. Okay, you cannot show uniqueness, you can show that it has at least one solution, UH. Okay? So the theorem, the main theorem that we would like to show here is the following. So I take U the solution of the nonlinear problem, UH the solution of the nonlinear problem in quadrature. Okay, I assume 1, 2, 3, which already I need to assume to have a unique solution. Okay, then I assume that the solution U is in HL plus 1 intersection with W1 infinity. AJ has some regularity that is written here. F has some regularity that is written here. Okay, the mu here is either 0 and 1, and depends if you want to have H1 or L2 error estimates. Okay, I didn't talk much about the F. So if you don't want to discretize the right-hand side with numerical quadrature, you can forget about the assumption here. Okay, that is only if you want to also discretize the right-hand side with numerical quadrature. And you need some bound on the coefficient. You need some bound on the derivative with respect to the nonlinearity of the coefficient up to 2. Okay. Then the result is the following. There exists an H0 such that for all H smaller than H0, the finite element solution UH of the nonlinear problem with numerical quadrature is unique, and we have this bound here. There is a side result. The side result is the following. If the coercivity constant times lambda 0 is the Lipschitz constant that we had, times the U, the second, the norm, H2 norm of U is sufficiently small, so a smallness assumption. The assumption W1 infinity and this assumption here can be removed. And as an immediate consequence, it means if you have a linear problem, this here is 0. So as an immediate consequence, for linear problems, we recover the estimates of Sierle-Raviard with the same assumptions. Okay, so our result is a strict generalization of Sierle-Raviard for nonlinear problems. Okay. So briefly, so we suffer a bit to do the proof for that, so I will not make you suffer. I will just write down 3 lemma. The first lemma is if you assume Q2, so that's an assumption on the quadrature formula, plus some convergence of the right-hand side. Again, you can forget about that. Suppose that you have no numerical integration on the right-hand side, so that assumption disappears. And here I just write this assumption because it's a much weaker assumption than the assumption that I have here. Okay, if F satisfies that, so that assumption is verified. Okay, so the first result, and that's in the spirit of Feistauer, he did even a stronger result, but he did this result only for piecewise linear elements. You can show that U minus UH converges to 0 for H goes to 0. Okay. The second result is if you assume the hypothesis of the theorem, you can show an H1 error estimate, optimal, but you have a tail here which depends on the L2 norm. The third result is that you can have an estimate in the L2 norm, which is optimal. Okay, you can have two different results. They have two different regularity assumptions, the two results, right? Right is why I put the two results here. One is with mu0, one is mu1, okay? You can have here the convergence rate, the L2 norm, with a tail, which now depends on the H1 norm, okay? So now from the first result, we know that this here converges to 0, but you don't know the rate because you don't know the rate of that, okay? But now we can plug this result here into here. Since we have an h, u minus u h to the square, and we know that it's converged, we can put that on the other side, and we have the convergence result, okay? And for the L2 estimates, it's trivial once we have the H1 error estimate because we know that H1 is constant times HL, so it's constant times H to 2L, okay? So I will not comment too much on that, but for example, this result here relies on the linearization of the problem, considering as one does when one wants to have optimal result in FEM Niche duality arguments. But here again, that was result which were obtained by Niche for indefinite problem, but we need indefinite problem with rational crime, indefinite problem with numerical quadrature, okay? So these results also of Niche have to be generalized to obtain the lemma tree. Okay, so lemma 1, 2, 3 gave the theorem rate of convergence, and then we can show that the Newton method to compute UH is well defined and converge, and this gives uniqueness. Okay. Okay, let me give an example. So the example is the Richards equation. Okay, that's infiltration of water in an unsaturated medium. I will take the stationary case. Okay, that's the case that I considered. Here U is the pressure, theta here is the water content, okay, and okay, I take some initial and some Dirichlet and Neumann, tie boundary condition, okay, and that's what we obtained. So the level curve for increasing macroscopic mesh size, and that's the convergence plot that we have. So for the error, okay. In case of piecewise linear elements, so we have H2 convergence in the L2 norm and H1 convergence in the H1 norm. Okay, so don't have much time. I would like to mention how that can be now transferred. This result for numerical quadrature can now be used to solve the multiscale problem, the full discrete analysis of the multiscale problem, and to in fact answer the different question that I have at the beginning of this talk. Okay, so I will not insist too much. I have here now the tensor which depends on epsilon. Okay, an oscillating tensor. I have also a notion of homogenized equation and homogenized coefficient, and that was derived, I think, first by Boccardo and Murat, and later on by Fusco and Mosca-Riello. Okay, so the players are as before. Okay, we have the macroscopic finite element method. Of course, now we have a nonlinear problem. But please look the way you write the method. The micro problem is linear. Okay, the micro problem is linear. So, but of course, we have a macroscopic nonlinear problem. Okay, so it's similar than before, and you can just consider the S here as being now parameters on which you solve your microscopic problem. When you need Newton iteration, this S would be the successive iteration for the UH solution. Okay, so we have linear microscopic cell problem and an overall nonlinear method. So the hypothesis, we take the same as the previous theorem, FEM with numerical quadrature for nonlinear problem, with AXS replaced by A0XS. I will call that capital H. Okay, so now we can go to the same lemma that I did before. So U minus U0, so UH is now the solution of the fully discrete FEHMM solution. Okay, so UH minus U0 and the L2 norm converge to 0 for H, and here I have an RHMM. We'll come back to that later on. That's the player that you have seen in the linear case. If that goes to 0, lemma 2, we have, again, the rate HL plus contribution of the L2 norm. Lemma 3, as before, we have HL or HL plus 1, and we have the contribution of the H1 norm, which comes with the quadratic power here. Okay, and our HMM now, it's the difference between the bilinear form, that's the FEM with numerical quadrature for the homogenized problem, and that's the full discrete bilinear form. Okay, so B0H is the bilinear form for the standard FEM numerical integration, the problem that we have just treated before. Okay, so the theorem now says you that if H0 is larger than 0, so for all H smaller than H0 and our HMM small enough, any solution UH of the FEHMM satisfies the following bounds. Okay, our HMM can be analyzed similarly as for linear problems. Okay, and finally, unicity, if R HMM plus R prime HMM, I will not go into details here, it's a condition which, when you do Newton iteration, you have to take the derivative, you have to take the derivative of your tensor, and the derivative of the tensor enters in the, we have a condition similar to that one, but with the derivative with respect to the nonlinearity. Okay, so if these two quantities are smaller than R0 prime and H is small enough, then again the Newton method to compute UH is well defined and converge, and the FEHMM has a unique solution. So let's see again this plot that I showed several times already for the convergence plot with respect to H1 and L2 error. Okay, here again you have the macroscopic degrees of freedom, which now go to left to right. Each of the different curves are for different microscopic resolution, and again we see that we need simultaneous refinement, and for that simple example we almost obtain the bound that we have shown before. Okay, so meaning that the discrepancy here is exactly for the L2 norm, where you have not enough point in the microscopic sampling domain compared to the macroscopic degrees of freedom. I take now the same problem as before, the Richards equations, but now with an oscillating tensor. Okay, so I have a new epsilon which comes into play. Okay, and here I see what happens for the solution. That's the level curve here of the pressure. Okay, and we see here for n macro, the macroscopic degrees of freedom are fixed, and the microscopic degrees of freedom are increased. Okay, with low microscopic degrees of freedom, you don't have at all the exact behavior, and then you see that when you increase the microscopic degrees of freedom, you converge to something which does not change anymore. And if you compare that to the reference solution, it behaves well. Okay, on that side of the picture, I just put a FEM finite element method with unresolved microstructure, again to stress that this doesn't give the right result. Okay. So let me I will end my talk in 5 minutes. So what is the message of this talk? We have seen that the analysis of numerical homogenization method, they rely on a priori estimates for FEM with numerical quadrature and strength type lemmas for estimating the micro error. Okay, and whenever the FEM with numerical quadrature is not available, this is a good, maybe a good idea to first derive this type of estimates before going to the analysis. I mean, it simplifies very much the analysis than for the multi-scale problem. That's the message. So the mesh size in macro and micro finite element method have to be refined simultaneously, and the complexity is super linear with respect to the macroscopic degrees of freedom. Okay, so now even that's another part of my research. So even though numerical homogenization methods are very efficient to solve multi-scale problem, there are many situations where even numerical homogenization is costly. Okay, so think a 3D problem, the problem that I showed before, the chip, for example. You have to have many repeated cell problem calculation, or problem more at 2 scale. Okay, so we have recently done the analysis for 3 scale problem, for example. There, of course, the complexity increases. You have to solve the microscale, the mesoscale, and the macroscopic scale. Okay, and you have to tune all the different meshes in order to have the good convergence result with the minimal computational effort. Okay, so I would like to give a few directions that we explored. So first of all, something that I didn't mention at all during these talks, that you could couple different methods at different scale. You could couple a finite element method, for example, with a spectral method on the microscopic domain. Okay, and that can give a very good result, but you pay because you need regularity on the microscopic problem. Okay, that may not be realistic for material science, for example. Okay, the other important point, I think, is adaptivity. Okay, so we started to develop these last few years adaptivity, and that's very important because you remember now that we have the linear form. It's based on the numerical computed tensor. Okay, and if you do adaptive methods, you don't need to recompute, you don't need to refine uniformly the mesh, and you don't need to recompute this numerical homogenized tensor where you don't want to refine the macroscopic mesh. Okay, and for many problems that is a huge saving. Okay, because you can recycle all what you did in the microscopic computation for part of the domain and just recompute new microfem where you need the accuracy, according to the macroscopic convergence rate that you want to obtain. Okay, so we have derived recently rigorous a priori and a posteriori bound for numerical homogenization. The other thing that we are exploring here is consider the cell problem as parameterized by the slope variable. So maybe you don't need to repeatedly do the cell problem in each macroscopic sampling domain, but you could use ideas from reduced basis methods to have a reduced basis for the microscopic finite element calculation. Okay, and that's related to a work that Sébastien Bourgeval did recently, and you have some work in progress related to that. Okay, with that, I thank you for your attention.
Is it also possible to reconstruct the effective coefficients and to get a priori error estimates for them?
Reconstruct the what?
The effective coefficients, A0 of X.
Yeah. Okay. Yeah. That's that's a side effect. That's a side result of the. In fact, when you do the FEM and you do the local assembly in each of the local elements, the contribution of the microscopic FEM, in fact, gives you a scaled value of the homogenized tensor. Okay, so you can just recover that in each of your sampling domain if you want, and you can have error estimates, and they depend, of course, on the accuracy on which you do the finite element calculation in the micro sampling domains. Yeah, you can do that.
Questions? Yes, actually. Isn't linearization at micro level for nonlinear problem? It goes back before Jin-Cha Shu. I mean, I think people who did homogenization of pseudo-monotone operators and all that, they used to just linearize U and grad U. I didn't know what you meant there, but
I meant analysis. I don't claim that that's not. Okay. I meant I want to do an analysis, but I just say that when you want to compute that, you should be aware that you can do the cell problem in a linear way. But even in the paper of Winan, I think they do that also. I mean, they write the cell problem in a nonlinear way, and during the analysis they transform it in a linear way. So I agree with you. I mean, it's not something at all original.
So one question is about the wave equation example. Is there prospects of getting a handle on the modelling error there if you're not representing the periodicity exactly on the scale?
I'm not there yet. I'm way away from that. I mean, what we like now to understand is to get the dispersive effect. So to get the higher homogenized model without deriving it beforehand. But that I don't know at all. I don't know at all.
While the action is cooking up, I have a last question. At some point, you stress that you have error estimates between the homogenized solution and the computed solution, and not the epsilon solution.
Yeah.
Can you comment further about that? Somehow you are not interested in the homogenized solution. You are interested in the solution depending on epsilon.
Okay, yeah, that's a good point. Okay, so the question is if I would like to have an estimate with respect to the fine scale solution, right? And the answer is algorithmic answer is that you can extend the microscopic solution that you have. You have kind of a corrector on the sampling domain, and you can extend that on the macroscopic element. Okay, and then you can have an estimate with respect to the fine scale solution in some cases. Again, in the periodic case, you can have something, an estimate which goes like square root of epsilon. Okay, so you have boundary layer terms which comes in. So that's an important point. So you can recover the fine scale information in part of the domain where you need, and you can, in some situation, have an estimate on that. So I didn't comment on that, but we have results on that as well.
Okay, thank you again for it.
Thanks.